Hi, everybody. So going to continue talking about the nomenclature of the chirality center. And remember, that's that CIPRS system. Last time we went through, I gave you the rules and we worked through a bunch of examples. And today I want to talk about how I alluded to the fact that sometimes we need a tiebreaker to decide whether the absolute configuration of a chirality center is R or S. So let's talk about that. The tiebreaker. All right, so imagine you have maybe something that looks like this. BR here and H there. All right, so this is definitely a chirality center because it's bonded to four non-equivalent groups. It's bonded to a propyl group, it's bonded to an ethyl group, to a bromo, and to a hydrogen. So that's a chirality center. And what we were talking about last time was that you start at the chirality center and then you jump out to the atoms directly bonded to the chirality center, and then you rank them in order of atomic number high to low. So bromine is definitely going to win because that's the highest atomic number, and hydrogen is definitely going to lose because that's the lowest atomic number. But now we have a crisis, because when we jump out to carbon on the left and jump out to carbon on the right, and so we have a tie. So we need that tiebreaker to resolve the tie. And what we do at this point is that we have to go to the next set of atoms. So this guy, that's a carbon. And this guy, he's a carbon. So at this point, we're tied. So now we have to go to now we have to use the tiebreaker, which is we go to the next set of atoms, tied. So what do? Go to the next set of atoms. And what is the next set of atoms? This is all atoms bonded to the previous set. Okay, so now in this example is that I'm currently at this carbon atom. I have to go out to the next set of atoms. And so this carbon atom, who is he bonded to? He's bonded to two hydrogens, and he's also bonded to a carbon. Okay, so his next set of atoms, written in order of atomic number, high to low, is a carbon and two hydrogens. Okay, so over here we do the very same thing, is that we have to go to his next set of atoms, which is everything that is bonded to this carbon. So I'm going to put his next set of atoms in circles. This carbon atom is bonded to a hydrogen, to two hydrogens, and it's also bonded to this carbon. So his next set of atoms, written in order of atomic number high to low, is once again CHH. So we're still tied because the next set of atoms on the left was equal to the next set of atoms on the right. Okay, so we'll call this we'll call this the next set. All right, so now what we have to do is we have to jump out yet again because we can't make a decision about R or S. And so we have to jump out to the next set of atoms. Okay, so that means everything bonded to the previous set. The previous set here was everything in a square. So, we're finished with this hydrogen, but this carbon, now he's bonded to a hydrogen, and I'm going to put his next set of atoms in double squares. And he's also bonded to this carbon. And I'm going to put him in double squares, just trying to show that this was the next set of atoms. So the second set on the carbon on the left here, everything in the box, everything in the squares with a double square was CHH, written in order of atomic number, high to low. Now we have to do the very same thing on the other side. Everything bonded to the circle. So that hydrogen, that was in the previous set, we're done with him. This hydrogen, that was in the previous set, we're done with him. Okay, but now this carbon, who is he bonded to? He's bonded to a hydrogen. I'm going to put him in a double circle to show this is the next set. He's bonded to another hydrogen. I'm going to put him in a double circle to show that he's in the next set. And he's also bonded to a third hydrogen. I'm going to put that in a double circle. So on the right-hand side, written in order of atomic number, high to low, this next set of atoms over here is HHH. Okay, finally, we can make a decision because we have these two sets of atoms, and the winner is going to be the set of atoms that has the highest atomic number atom at the first point of difference. Okay, so that sounds kind of cryptic, so let's try to unpack that. So what we do now is we compare this set atom for atom, one at a time, until we have a winner. We're looking for the highest atomic number atom. It's a carbon versus a hydrogen. This guy won. So this guy won, this guy lost. Okay, so now we're ready. So let's just restore this picture because it got very messy. Let's just restore this picture. One, two, three. Let's restore this picture. And so this was 1. This was 4. This road was our winner. That was 2. And then this guy over here, that was 3. And so with the group of lowest rank facing away from you, what is the sweep of the top 3 ranks? It is counterclockwise, so that this is the S absolute configuration, right? And this molecule would be called 3S, right? I'm telling you which carbon atom is the chirality center and what is the chirality of that chirality center. 3S, 3 bromo, 1, 2, 3, 4, 5, 6, 3 bromo hexane. Okay, so that's the implementation of the tiebreaker, is that you start at the chirality center, you jump out one atom, but if you can't make a decision, then you have to look at all of the atoms that were bonded to that atom that you jumped out to. And then if you can't make a decision, you have to keep on going. All right, so let's try this a couple more times. All right, so if we have a, if we look at this chirality center here, let's say CH3, H, Br, maybe something like that. All right, so here's our chirality center. We jump out to the next set, we jump out to the atom directly bonded to the chirality center and rank them in order of atomic number, high to low. So we're starting here. and we jump out to fluorine, jump out to carbon, jump out to hydrogen, and jump out to carbon. So we have a tie because this carbon atom and this carbon atom, they have the same atomic number. We need that tiebreaker. But we know that fluorine is going to win. That's going to be 1. Hydrogen is going to lose. That's going to be 4. That's a carbon. That's a carbon. Now we have to look at the next set of atoms. Who is this carbon bonded to? He's bonded to 3 hydrogens. And we write his next set of atoms in order of atomic number, high to low. What about this carbon here? Who is he bonded to? Well, he's bonded to a bromine and 2 hydrogens. We're writing his next set of atoms in order of atomic number, high to low. And now we compare each set of atoms, and the winner is the set of atoms that has the highest atomic number in at the first point of difference. So we're comparing each of these numbers one at a time. It's an H versus a BR, the BR won. So this is going to be rank number 2. This is going to be rank number 3 because the BR beats the H. And with the group of lowest rank facing away from me, I see that this is going to be a clockwise sweep. So this is an R absolute configuration. All right, so that's the implementation of the tiebreaker. You're jumping out from the chirality center to the atoms directly bonded to the chirality center. And then if you can't make a decision there, you have to go out to the next set of atoms. Okay. So now let's talk about something, another level of complexity with the Kahn-Ingold-Prelog system, and that will be the treatment of multiple bonds. And we can summarize how a multiple bond is treated in one pithy little sentence, and that is a multiple bond is treated as an equivalent number of single bonds. So whenever we're looking at a multiple bond and we're trying to decide the R and S of the chirality center, we have to deconstruct the multiple bond into an equivalent number of single bonds. Okay, so let's look at an example. So something like, let's say, all right, so I want my chirality center here. All right. Okay, so there's a molecule that has this chirality center. We want to determine whether it's the R or the S absolute configuration. So we start here and we go out one atom, oxygen, hydrogen, carbon, and carbon. We're going to need that tiebreaker because we jumped out from the chirality center and we hit carbon going to 12 o'clock and we hit another carbon going to 4 o'clock. But this much we know is that oxygen is going to come in at number 1, hydrogen is going to come in at number 4, but now we have a carbon versus a carbon. But the extra complication that I'm talking about here now is that this carbon is bonded to an oxygen by a multiple bond. Okay, so this guy would be treated as if it were the following. Okay, that's a single bond, we don't do anything. That's a single bond, we don't do anything. That's a single bond, we don't do anything. Okay, but now this carbon here, he's bonded to an oxygen, but by a double bond. So in the Kahn-Ingold-Prelog RS system, what we do is we decompose, we deconstruct this carbon-oxygen double bond as if it were two carbon-oxygen single bonds. So we have a carbon there, and this carbon atom, I'm going to put a C there, this carbon atom is bonded to an oxygen, but he's bonded to that oxygen by a double bond. So what we have to do is deconstruct this double bond into two carbon-oxygen single bonds. So this carbon is imagined to be bonded to a second oxygen that's not really there. It's there for bookkeeping purposes only. And lots of times, these imaginary oxygens, these are called phantom oxygens. They're not really there. They are there for bookkeeping purposes only. And frequently, maybe you'll see a little dot or a little zero there showing, well, that's a phantom oxygen. Blah! This oxygen is bonded to the carbon also by a double bond. So we have to deconstruct the multiple bond into an equivalent number of single bonds. So this oxygen is bonded to a real carbon, but it's bonded to that carbon by a double bond. So we have to give this oxygen a phantom carbon as well. Okay, so that's the deconstruction of the multiple bond according to the Kahn-Ingold-Prelog system. So notice that this carbon atom is bonded to a real oxygen and an imaginary oxygen. That's the carbon-oxygen double bond. And this oxygen, he's bonded to a real carbon and to an imaginary carbon. That's the carbon-oxygen double bond. Okay, so now finally and at last, we're ready to rank. So oxygen comes in at 1. Hydrogen comes in at 4. That's a carbon, that's a carbon. We're tied. We have to go to the tiebreaker. This carbon is bonded to an oxygen and 2 hydrogens. That's his next set of atoms. I'm writing the next set of atoms in order of atomic number, high to low. This carbon, who is he bonded to? What is his next set of atoms? He's bonded to a real oxygen, an imaginary oxygen, which counts exactly the same as a real oxygen. It's just there for bookkeeping purposes only, and he's bonded to a hydrogen. So now we can finally make a decision, because now we compare these two sets of atoms. These were the next set of atoms. We compare these two sets. The winner is the set that has the higher atomic number atom at the first point of difference. So it's an oxygen versus an oxygen. We're tied. We have to go to the next set, the next atom in each set. It's a hydrogen versus an oxygen. This is a phantom oxygen. It's not really there, but it counts exactly the same as a real oxygen. So this guy wins. He's number 2. That's number 3. With the group of lowest rank facing away from you, the sweep of the top 3 ranks is clockwise. This is an R absolute configuration. Okay, so that's the treatment of the multiple bond, and also this was another opportunity to use the tiebreaker. So let's look at a couple more examples where we're dealing with the multiple bond. Okay, so let's imagine that this guy here, that's our chirality center, right? I'm just going to put a little star there. That's a chirality center. And let's say he's bonded to the cyano group. How would we deconstruct this cyano group according to the rules of the CIP system? So this cyano group, he's treated as if he were, there's the chirality center, This carbon is bonded to a nitrogen atom, but it's bonded to that nitrogen atom by a triple bond. So that carbon nitrogen triple bond has to be deconstructed into 3 carbon nitrogen single bonds. So I need to give this carbon a phantom nitrogen. I need to give this carbon a second phantom nitrogen. And these little dots mean that those nitrogens aren't really there. They're just there for bookkeeping purposes only, but it doesn't matter. They count exactly the same way as a real nitrogen. So you see how this nitrile carbon, it's a triple bond to nitrogen that has been deconstructed into 3 carbon nitrogen single bonds. And now we have to do the very same thing with this nitrogen over here, because he's bonded to a carbon, but he's bonded to a carbon by a triple bond. So we need to deconstruct that triple bond into 3 carbon nitrogen single bonds. That means giving this nitrogen atom a phantom carbon and giving this nitrogen atom a second phantom carbon. So we see the 3 carbon nitrogen single bonds into which the carbon nitrogen triple bond has been deconstructed. Okay, so let's see, maybe try this again for what about something that looks like a this. Okay, so now how would we deconstruct that? The star, that's the chirality center, and this would be treated as if it were, there's the chirality center, we're off to this carbon. This carbon is bonded to another carbon by a double bond. So there's the real carbon atom, but we have to deconstruct that carbon-carbon double bond into 2 carbon-carbon single bonds by giving this carbon a phantom. And this carbon over here, he's bonded to a carbon also by a double bond. So we have to deconstruct that double bond into 2 carbon single bonds by giving this carbon a phantom. All right, and so now this carbon up here, he's bonded to 2 hydrogens. And this carbon down here, he's bonded to a carbon, and that carbon is bonded to 3 hydrogens. So that's the deconstruction of that group according to the Kahn-Ingold-Prelog system. So now, as confusing and as weird as this may seem, it does make some sense when you think about it this way. Carbon forms 4 bonds. We're just trying to deconstruct, we're trying to recast each carbon so that it has 4 bonds, but they will be 4 single bonds. You see how this carbon here is forming 1, 2, 3, 4 bonds. This carbon down here is forming 1, 2, 3, 4 bonds. Same for this carbon up here. Nitrogen forms 3 bonds, but in the deconstruction, we are recasting each nitrogen into 3 single bonds. And so this nitrogen is bonded, has 1, 2, 3 bonds. Phantom atoms, they're dead ends, right? This is a carbon, I don't see 4 bonds. So that's how a phantom atom is different from a real atom, in that this phantom atom, we're not giving him 4 bonds, right? The phantom atom, that's the dead end. He's just there for bookkeeping purposes only. Okay, so that's how we treat the multiple bond in the Kahn-Ingold-Prelog system. All right, so let's do some problems where we're getting into that double bond and maybe getting into that tiebreaker as well. All right. So let's figure out the chirality of everything here. Anybody recognize this molecule maybe from your other courses? Maybe you can tell me in the chat if you recognize this molecule. Maybe you've seen it before. Oh, it's a biggie. It's one of the most important molecules ever. Anybody recognize it? You can tell me in the chat if it looks familiar. Okay, I guess not. This is 2-deoxyribose. This is the carbohydrate residue in DNA. And God knows you can't get more important than DNA, right? How many chirality centers? 3 chirality centers, right? There's 1, there's 2, there's 3. 3 chirality centers. Let's figure out the absolute configuration of all of them, right? The most important molecules in biochemistry and in organic chemistry are loaded with chirality centers. And this is the carbohydrate residue of DNA has 3 chirality centers. Okay, so let's go for this one first. Let's go for this guy here first. My pen is pointing to it. Tell me what its absolute configuration is. Tell me here in the chat, right? You have 50-50 chance of being right just by guessing. Okay, so this chirality center here, this is going to be the R absolute configuration. Okay, so let's see how we came up with that. So that's the chirality center. We're jumping out to the atoms directly bonded to the chirality center. It's a carbon, it's a hydrogen, it's an oxygen, and it's an oxygen. Oh, we're going to need that tiebreaker because we have oxygen on the left and oxygen on the right. But we know that the hydrogen is going to lose. Hydrogen's going to lose. And one of these oxygen is going to get the gold, and one of them is going to get the silver. We don't know which yet. But this carbon atom, he's going to be number 3. Okay, so now here's an application of that tiebreaker. That's an oxygen, that's an oxygen. We have to go out to the next set of atoms. This oxygen, he is bonded to a hydrogen. This oxygen, he's bonded to a carbon. Those are the next set of atoms that we need in the tiebreaker. So that we look at these and we compare them. The winner has the higher atomic number at the first point of difference. So carbon has a higher atomic number than hydrogen. So this guy is 1. This is 2. And now with the group of lowest rank facing away from you, which it is, the sweep of the top 3 ranks is clockwise, so that this guy here is an R absolute configuration. Okay, so let's go for the other chirality center. So now that's very, very messy. How about we just draw a new molecule? Just make another one. All right, so let's go for this chirality center over here at 10 o'clock. All right, this chirality center right here. Tell me, what is its chirality? Tell me in the chat. Is it R or is it S? Okay, so this guy, he's going to be the another R absolute configuration. Okay, so we're looking at this chirality center. We see oxygen, hydrogen, carbon, and carbon. So we need that tiebreaker again. Hydrogen will lose, oxygen will win. This carbon atom, his next set of atoms, who is he bonded to? He's bonded to an oxygen and two hydrogens. So that writing his next set of atoms in order of atomic number, high to low, it's OHH. Okay, this carbon, what is his next set of atoms? He's bonded to an oxygen, a carbon, and a hydrogen, and writing his next set of atoms in order of atomic number, high to low. This carbon is bonded to an oxygen, a carbon, and a hydrogen. And so we can make a decision now. So we have oxygen versus oxygen, tied. Look at the next atom in each set. The winner has the higher atomic number atom at the first point of difference. It's a hydrogen versus a carbon. This guy won. Okay, so this is going to be 1. This is going to be 2 down here. And that's going to be 3 over here. And with the group of lowest rank facing away from you, you get a 1, 2, 3 clockwise sweep. So once again, this is another R absolute configuration. Okay, so let's go for the third and final chirality center, and then let's do a practice problem with a multiple bond. And then we'll get to the quiz. Okay, so now we're going for this chirality center right here at 8 o'clock. Okay, so tell me in the chat, what's he going to be? What's it going to be? All right, so this is going to be an S absolute configuration. All right, so let's see how we came up with that. Oh, there's a hydrogen here, right? Can't forget about him. And so that hydrogen lives on a wedge. Okay, so now let's rank. It's an oxygen, that's going to win. It's a hydrogen, that's going to be number 4. It's a carbon to the right, and it's a carbon going up. We need the tiebreaker. So we need to look at the next set of atoms. This carbon, his next set of atoms, written in order of atomic number, high to low. He's bonded to a carbon atom up here at 2 o'clock and 2 hydrogens. That's his next set of atoms. This carbon, his next set of atoms, he's bonded to an oxygen, a carbon, and a hydrogen. An oxygen, a carbon, and a hydrogen. The winner is the set of atoms that has the higher atomic number atom at the first point of difference. So we compare each of these atoms one at a time until we can make a decision. It's an oxygen versus a carbon. This guy won. Okay, so this is going to be 2. This is going to be rank number 2. And this is going to be rank number 3. And now with the group of lowest rank facing away from you, but it isn't here, it's facing toward you. But last time we talked about a little trick that we can use when the group of lowest rank is facing you, you note the sweep of the top 3 ranks, and then you reverse it for the right answer, because when the group of lowest rank is facing you, you're looking at the molecule backwards. So the group of lowest rank here is facing me. The sweep of the top 3 ranks appears to be clockwise, but I'm looking at the molecule backwards. Reverse it for the correct answer. So this guy is an S absolute configuration. Right, so how'd that go? Yeah? All right, so now let's try an example with a multiple bond in it. Okay, so tell me about that chirality center. What is it? Is it R or is it S? So this guy right here, what's he going to be? He's going to be an S absolute configuration. Okay, so we have this multiple bond, and so we remember that this is treated as if it were, I'm going to draw a big picture down here. I think you're going to need it. This carbon is bonded to a real carbon, but by a triple bond, so we have to deconstruct that into 3 single bonds to carbon. This carbon is also bonded, he's bonded to a hydrogen, but he's also bonded to a carbon by a triple bond, so that triple bond has to be deconstructed into 3 carbon-carbon single bonds. So I've added all of these phantom carbon atoms in order to for the bookkeeping. Okay, now we're ready to rank. Oh, and we're going to need that tiebreaker because I'm here at this chirality center and I see hit carbon, carbon, and carbon. Right? We have a 3-way flat-footed tie. So we have to look at the next set of atoms. This guy over here on the left, his next set of atoms is CHH. He's bonded to a carbon atom and 2 hydrogens. This carbon atom over here, his next set of atoms is HHH. This carbon right here, his next set of atoms is C, C, C. So 2 of those carbons are phantoms, but a phantom ranks exactly the same as a real carbon atom. So now we're ready to make a decision. We look at each set of atoms, and the winner is the set of atoms that has the highest atomic number atom at the first point of difference. It's a carbon versus a carbon versus a hydrogen. We're looking at the first letter, right? So hydrogen is going to lose, and this HHH set, that's going to come in at number 3. All right, but this set is still tied with this set. We look at the next atom in the array, and it's an H versus a C. That's a phantom carbon, but it counts the same. So this guy wins. He's number 1. There's number 2. The group of lowest rank is facing away from me. That's an S absolute configuration.